The purpose of this video is actually to talk something about concept of the imaginary point for last lesson, and then to give you a concept of streamline and pathline. So after that we'll talk about in-depth of streamline and pathline. So without further ado, we shall start. So if you remember last week, okay, we have this curved surface. You're taught to find the force, okay. And you remember if we actually do this example, okay, if you remember. So you have the B, we took reference of point B and reference of point A and D and E. Why didn't we take the reference to from point C? Because it's an imaginary point. So if let's say in a physical world, you try to describe certain things, certain dimensions, you take reference from point C, but however in point C there is no point C in the real life, because point C is just a point stating the same point, I mean same height of B, but rather it doesn't exist at all. So typically if you were the constructor of whatever shit, um you have to take reference to B, A or D or E, type of thing. So C itself is an imaginary point, so therefore it is wise if you don't take this point as a reference, but rather you take this point B or perhaps D or E, maybe. But nonetheless, B and A are the most good point to actually take off. So this will totally end the lesson 4. Nonetheless, we have a dam. This question I haven't do yet, so maybe in the future you do. But then we'll talk about flow visualization using streamline and pathline, and then solve some equations. So pathline itself is a trajectory of a fluid particle. So you have these 4 particles over here. At time 0, it's this position. At time 1, it start to move. At time 2, it start to move. Time 3, it move into a position. So typically, it's very, very tough to actually capture the movement of the particle itself. So actually, because you have to say that at time 1, what is the position over here? You can't find, right? Because they are traveling at velocity. So the fluid itself are traveling at velocity, which you have to first capture its point of velocity first. So let's say at this point the velocity is in the x-axis is dx dt is equals to u, while the v is equals to dy dt, which is the y-axis. While u and v has some equations, maybe some x, maybe some 2y plus 3c or whatever shit, but it is some equations for u and v. In the later videos we'll talk about it. So why they actually say that we actually use two-dimensional, why we actually use this differentiation, this velocity to to help us find our segment points, because the fluid itself, the particle itself is moving. So let's say we capture the point at this timing, and then we can use this equation, and then we can do some magic, integrate it, and then we can actually have a equation that can describe the position at x and the position at y, and then you just plot it out with a graph paper, so you can know at x what point and at y what point. You know that this point is this point over here. So just talking, but nonetheless, as you know, if you were to plot one point over here at time 1, one point over here at time 2, time 3, and time 4, eventually you have a time 5 and time 6, you can actually plot a path line. So the path line states what is the path that this particle took. So this is just a simple talking about it. So streamline itself is the tangent, okay, the gradient of the curve at every point, okay, the curve at every point, okay. So it's let's say this point is going this direction, so the 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 streamline itself is parallel to your wherever your vector, okay, your vector field is moving. So if you were to watch my video previously, okay, so not my video, not someone's video, okay, where you can come here, you put inside playlist, and then this is the vector field, right? So the green color is the vector field, while the black color is the streamline. Okay, so if you were to
There's our streamlines again in black, but now I've released 4 different particles, marked particles, and calculated 4 different path lines as a function of time. 1, 2, 3, and 4.
so this particle actually move, okay. So the tangent itself, okay, as you can see at the head of this particle, it is always tangent, is always somewhat parallel to the streamline itself, as you can see.
And you can
So as you can see, it is still in the
see they
parallel
follow
to
along
the
these red trajectories.
you see it is still parallel to the head itself, okay. It's still parallel to the streamline, and the streamline itself is parallel to the vector field. So they are all you know so just talking about the behavior of streamline. What is actually streamline? So streamline is governed by a formula dy dx is equals to v over u, which comes from this v divided by this u. Okay, so you eventually you get this one. And then although this may seem pretty easy, okay, um, nonetheless it's very easy, but there is a secret weapon, which is this one. Okay, this one we didn't go through much in class, so I realized I thought that I need to talk about it. So maybe hold a while. So we actually talk about the v divided by u is equals to dy dx, right? So the v itself, as you know, is equals to dy dt, and u equals to dx dt, given in this portion over here. Okay, for the path line with the velocity of the particle. So if you take v divided by u, okay, this is a simple math. Okay, just proving. So you dy divided by t divided by dx divided by t. You cancel out the dt's, you get dy and dx. So you get dy over dx. So with this concept, we will go to the understanding for the where am I? For calculating the more difficult streamline. Okay, so last part we actually talked about v divided by u equals to this, right? So if you to bring this thing out, if you were to solve using separable equation, because we are now talking about two 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 variables dx and dy. So if you want to solve it, you can actually solve using dx and dy. You just bring this dx upwards, then you bring dy, you have this one. And then in order to because u and v has some equations, as I said earlier, u and v may have some equation, maybe e t and maybe x, and then v, this is v, and maybe u is equals to a e t y x. Who knows? Okay, so similar. So what we are doing is actually trying to derive an equation, general equation. So this general equation is pretty tricky, but apparently what you need to know is actually this one also. Okay, so u dy minus v dx equals to 0. So if you were to look at this thing, do you find that it is an exact equation? Okay, since that u dx is equals to u dy, so just bring this over, it's actually their exact equation. So definitely u and v, they have some relationships, okay, such that when you integrate, when you solve using exact differential equation, you can eventually find things. So eventually u is actually equals to partial xi divided by partial y, while minus v, okay, minus v over here is equals to partial xi over partial x. Okay, so this is a very key term I want to convey. Okay, nonetheless, you may ask me why can't it be like this? Okay, so what I mean is, let's say instead of bringing the v over here, I bring the u over here. Right, so this one will become minus. But you can also do that, but the typical terms is that they actually bring the v over here. So everybody are using this, so don't be, so you just use this kind already. So why u is equals to partial xi over partial y? Okay, so I hold on. So let's say if you have an example, we have a xi is equals to xy plus y square. Okay, this is the equation, we call it xi. And if you to differentiate this d xi, typically you have to differentiate the y and differentiate the x. So apparently for this xi, d xi divided by dy, you have if you were to differentiate y, you have x, and then dy, right? Then plus, if you differentiate dx, there is no dx. So you have, maybe perhaps I should put it x squared. Yeah, okay, anyway. So if you differentiate dx, you'll get 2x dx, right? So, sorry, you will have 2y done bar. Okay, sorry. You will have 2x y squared dx. Like if you want to remember, so yeah, just simply differentiating it. Okay, differentiating the xi in order to have a this portion over here. Another question is that you may wonder why if you differentiate dy you have x dy. Okay, so for example you have an equation, let's say xy plus x squared y squared is equals to xi. So if you imagine you have so imagine if you were to differentiate in terms of y, you have x left over, right? So x is equals to maybe I should, because now we have y squared, so it's x plus 2y x squared. Okay, so yeah, hold on a minute. Yeah. Okay, so this should be the equation after we derive the y over dy, because now we add in x squared over here, right? Because yeah, anyways, let's go back to here first. So the reason why I explain why this is dy over here after you differentiate dz over dy is because let's say, as I say earlier, you have this equation over here, right? The same thing as here. As that let's say you have to differentiate this, so you have dz dy is equals to x. Okay, because I differentiate away that y, so plus 2y x squared, right? So dz, as you can see, dz is over here. So dz is equals to x plus 2y x squared. Then you bring this dy up. So nonetheless, for dx, the same thing applies. So this is how we have this. As you can see, our dz is divided by dy, right? So you can say that it's a partial xi partial y in a sense. So in this case, this is why if you take this as u and you take this thing as minus v, okay, you have this equation. So this one is actually equals to u, or this one in another sense is actually equals to minus v from this definition. Okay, from this definition, minus v is always equals to this. Okay, so you may feel a little bit weird, but you just accept it lah. It's quite natural. It comes like this. And then if you want to describe this equation using these definitions, so this is how I describe. Okay, so I can't prove to you because I can prove to you that v minus v, okay, I can't prove to you that this one is xy and this one it's I mean I can't prove to you that u is equals to xy and minus v is equals to x squared y squared, because you don't have any meaning at all. But nonetheless, I have proved to you that partial xi divided by partial y dy. So this one. So in other words, this one is equals to this one, while this one is equals to this one. Okay, so equals to dz. So from later, you actually see that we will be using this formula later. So actually, this is also from your text itself. We actually derive, and you can see also that we actually set u is equals to partial xi divided by partial y. So as you can see, the definition for u in this, the definition of u and v has changed from what we have known for the path line. Okay, so be very careful when you know which u and v are doing. Okay, so u and v for this case is a velocity thing. However, for this u and v is I have no idea. But nonetheless, I think they are quite related, but I can't explain it that in depth. But nonetheless, this is a very key understanding for the future part of the videos. So in the next video, we'll talk about actually deriving a general equation for the streamline. So we'll actually, this is the one that we talk about it, right? So later we'll do. Actually, I haven't finished yet. So maybe in the next video I'll just talk about it. Okay, so I'll see you in the next video.